Page number 45. Fine. Now this vectors, that's not what we want. It's 39, I want 45. Oh, I think that's the direct data function. Fine. Okay. So let's start the one-dimensional direct delta function. Wait, this is the one-dimensional one. Okay, I just want the direct delta function. So it starts off with the divergence of r hat upon r squared. Consider this vector function. Okay, at every location, v is directly related outwards. If there was a function that ought to have a large positive divergence, this is it. And yet, when you actually calculate the divergence, you get precisely zero. I mean, that's not quite how divergence is defined. It's not just that if the thing is like going out, then its divergence is positive. No, like what if you have a flow like this? So if you talk about fluid flow, then there's like all of these u vectors pointing the same direction. Then of course the divergence will be zero. And although like things are moving away from this point in this direction, there are things moving inside as well. So yeah, it cancels out. So the flux is still zero. Similarly, for some certain volume over here, you have a bigger magnitude over here, right? So the speed of the particles flowing in, that's bigger, although your cross-sectional area for this volume is lower, right? Over here, the area is bigger and the speed is lower, right? So that's why it cancels out and your flux is zero at the end. So that would be stupid if somebody like thought that divergence is going to be positive just because the field is radially outward. That's stupid. Okay, right. So you just get precisely zero. Got it. You will have encountered this paradox already if you've worked problem 1.16. Right. The plot thickens if you apply divergence theorem to this function. Right. So this thing. Once again, you cannot apply this thing because when you will do the volume integral of divergence, you will have to include the origin as well. And at origin, it's not defined. I mean, the divergence goes to infinity basically. So it's not defined at the origin. So you cannot apply the theorem because that requires some conditions and those conditions are not met over here. Okay, but the volume integral, this is 0 here. Okay, yeah, I mean this thing. So the flux is 4 pi, but the volume integral is supposedly 0, although we know that's not quite the case. Okay. So what it says is that since the divergence at your, what do we call it, at your origin is infinity, what we can say is that your divergence is actually a function that is zero everywhere else and it goes to infinity as your x vector approach or r vector approaches the zero vector, right? Okay, so a function like that is called a direct delta function. So he basically tells us how this thing will work for one dimension. So a direct delta function would look something like this. It's going to infinity as we get closer to the origin. Over here it's zero, and then you have this kind of smooth curve, but actually it's not supposed to be like that. You should have zero over here as well, right? But yeah, whatever. Okay, in the mathematical literature, it's not a generalized function or distribution. It is what if you like the limit of a constant sequence of functions. Okay, whatever. Oh, so you can also have direct data functions like this. So the thing about direct data functions is that their area is finite. So for example, this one has area 1, but their value at 0 is infinite, and everywhere else the value is 0, right? And in the proximity of the origin, you have some weird stuff happening, like the value is not exactly going to infinity, but then the value is like, yeah, our x values are so close to 0 that you cannot actually define the function for those values since you don't know what these values actually are. It's a limiting case in the end, right? So that's what he says, that the direct delta function is a limit of a certain function that has a constant area, and your f of 0 is approaching in, I mean going to getting bigger and bigger as your sequence moves on. So the limit as n tends to infinity of this sequence, at the end you should get the direct delta function. Cool. So you can have it like this rectangular stuff, right? Or you can have this thing. So yeah, this is our function. Like from negative 1 upon 2 to negative 1 upon 4, your function is 1, then it's 2, and at this point we don't know what exactly is happening, whatever. Over here it's like this linear function and stuff, and then you have to, keep on increasing the number of rectangles so that this rectangle gets more and more height, and then eventually it will go to infinity. There you go, you got your direct data function in that way, right? Okay, in fact, just to be on the safe side, let's say that f of x is continuous, then the product f of x del x is 0 everywhere except at x equal to 0. Okay, it follows that this thing, okay, whatever. So most important fact about vector functions, you should understand why it's true since y is whatever. Yeah. Okay, so this is an important fact. They are saying that right. Okay, guys, starting to understand what's going on. Right. So the integration in a region that contains this spike of the direct delta function times some other function which has some finite value in that interval, well, that integration is just going to give us f of x times del x at that x value, right? So why is that the case? Well, if your f of x was 1, then of course this would be, I mean, pretty obvious. But if it's not that, if it's something else, so let's just say f of x is equal to something like, so some constant, or we should just say f of, well, since we know that the delta function is having the spike at 0, so we'll just say f of 0, right? Okay. So f of x is equal to f of 0 plus some small change in f because of changing x. So we'll just call it like del f as a function of x, of course. So this del f thing is a new function. Right, so as x changes, this thing changes. You could linearize this thing, so to a first degree approximation, what you just get is like our f of x is just f of 0 plus partial upon partial x of f of x, or in this case we could just say d upon dx, right? And yeah, this is exactly the same thing as Taylor series, but okay, and it's at 0, I guess. Yeah, so this derivative at 0, and this times x. So first degree approximation, you can say that your f of x is something like this. Then there's like other terms with x square and whatnot. So if you do this thing times del of x, so the delta function, I think we should not be using this symbol. It's usually used to represent infinitesimal values. In this case, it has a completely different meaning. So just f of x times this function del of x. This is del, right? Or is it some other thing? I don't know. Don't call it del. Right. So this is equal to what? Is approximately equal to f of 0 del of x plus this thing. So you got like f dash of 0 times x del of x. And then you want to integrate this thing. Well, this one is the easier part. F of 0 is a constant, so just integration of this thing, that's just going to be so we already know that the area is just 1, right? So this integral will just be 1, so you get like f of 0 plus this part. So f dash of 0 is a constant, it comes out. What you get is like x del x. What does this become? Well, x is close to 0, and we know that like x is between, what was I going to say? This is slightly weird. I guess that's not the equality that we want it to be having. Okay, let's just say that del of x is this limit. Okay, that's also not going to work because the maths behind that, you'll have to interchange limits and stuff, right? Yeah. So suppose this function, I know it's supposed to be limiting case, but like let's assume it's not the limiting case yet, and this function is like this. So it has uh, you know in this range this function exists. Outside of it it's just 0, right? That's how del of x is. Now let's just say that this range is like going from, I don't know, like negative h to h, right? Then your y equal to x graph would look something like this. So I mean, why am I even drawing it? We know that x is less than h throughout this interval, right? So you can say that x del of x is less than, and our del is of course positive. So basically what we get is like this is less than h del of x, and it's bigger than negative h del of x. And then when you integrate this thing, you know that this will just be like negative h, this will be h. And since we said that h is like approaching 0 or something like that, you could basically say, yeah, this thing, the integral of that thing, of course, just going to write it like this thing. Very informal, but whatever. So it's between h and negative h, and these approach 0. So guess what? This thing approaches 0 as well. So this other part, we don't really care about it. Just plus 0, or whatever. And yeah, since we are dealing with infinitesimal quantities in the end, we just say that this guy's integration is going to be equal to f of 0. Right. That should do it. So we just proved that, I shouldn't say proved, but I gave you an explanation of why this could be the case. Right. Yeah, so you just get f of 0, right? That's what integral will give you. And of course, it's 0 everywhere else. It's exactly 0, not approaching 0. It is 0 at that, after this interval, it is 0. Before this interval, it is 0. It's not like it's approaching 0. It is 0. So that times of f of x, that will be 0 everywhere. So it doesn't matter even if f of x is like going to some, like infinite value or something, like f of x is a graph like this. That's how f of x is. It doesn't matter. In the end, it's 0 over here, right? Our del is just 0. So f times del, it's 0 as well. So the integral is also 0, right? I mean, it's defined to be 0. It's just the way it is. Yeah, I mean, look at this. Look at this. Over here, it was 0 from the start. We never said that it's approaching 0 or something like that. Yes, we said it's a limit of a sequence. Like this function is the limit of a sequence, but throughout the sequence, this was still exactly 0. So we don't have to worry about this integral giving us anything. Like f times del. This guy's integral outside of this range where f is going to this infinity thing. Outside of that, it's just 0 throughout, so we don't have to worry about that giving us some kind of finite value. It will be 0, right? Okay, so that's the direct delta function. So because of this nice property, like what we can say is that the divergence of our function r hat upon r squared, the divergence of this thing, you could say that this thing will be like 0 everywhere other than origin, and at origin it's going to infinity, but then the volume integral of this thing, that is 4 pi, we know that's the case, right? So you can define like a direct delta function which, or something like something times that, in fact I should say. Okay, that's for one-dimensional function. I think we need a three-dimensional function as well, right? Yeah, I mean, it's pretty much the same value, but slightly different, right? So it's like in 3 dimensions. So you are considering a volume integral that way. Okay, well, that was only one-dimensional functions. I think this book will explain three-dimensional functions soon. So first, let's solve some problems. This will be like some kind of delta function, right? Delta 3D, I don't know, of R. I don't know what this will be. We'll see what that is going to be. Okay, let's solve some problems now. Okay, evaluate this integration from 0 to 3 of x cube del of x minus 2 dx. So basically just plugs out the value at 2, because everywhere else this del of x minus 2 function is 0 other than 2, of course. So everywhere else is just 0, so we don't have to worry about those intervals really. We just have to worry about the interval in which you have this spike of a function, right? Our delta function is defined in that interval, which is also going to 0. Actually, it's approaching 0. So the integral in that interval, that will just give us the value of this function x cube at that interval. I'm saying at that interval and not like the value at some point in the interval, because at throughout that interval it will be constantly the same, approximately constantly the same value, because the interval is very small. So it just takes the value 8, and all you get is like 8, because this guy's integration, so the integration of del, that will be just 1, right? Yeah. So what you get is 8. That's what this integral is going to be. Oh, this was an example, I think. It's not a problem. Fine. Alright, that's it. The integral is 8. Sure. Notice, however, that if the upper limit had been 1, so 0 to 1, yeah, then it would be 0. The answer would be 0 because pi could not contain your, point 2. Okay. Although del itself is not a legitimate function, I guess not. Yeah, because it's like a limit of a function, limit of a sequence, something like that, right? Yeah. So you can't actually define what this is going to be in normal elementary functions. You can't do that. You can't do addition, subtraction, multiplication, and there you go. You got a function. You can't do that. You'll have to take a limit to actually define this del operator, to define this del function, which makes it not a normal function at least, right? Integrals over del are perfectly acceptable. In fact, it is best to think of the delta function as something that is always intended for use under an integral sign. In particular, two expressions involving delta function, say d1 of x and d2 of x, are considered equal if, what's this thing? Okay, this is true for all ordinary functions of x. Huh? So these two are delta functions, huh? Okay. So if this thing is true, then the expressions involving the delta functions. Wait, what? Sorry, I didn't catch that. What are they saying? In particular, two expressions involving delta functions are considered equal if this happens for all ordinary functions. Okay, okay, I got it. That's like same as saying that del like d1 equal to d2. No, no, it's not, because their shape might actually be different. Yeah, that could be a thing. Their shape might be different, and because of that, they are not actually the same function, right? But yeah, they behave in the same way. Okay, cool. Whatever. Show that del of kx is equal to 1 upon k del of x, where k is any non-zero constant. In particular, del of negative x is equal to del of x. Oh, it's 1 upon mod of k. Fine. That's an example, by the way. It's not a problem. For an arbitrary test function, if x consider this integral, change variable. Wait, what are we doing exactly? We let y be equal to kx. So now you just got like del of y over there. Got it. Ha ha ha. Right. What does it actually do? It gives us this thing. Okay. So it's the integral from negative infinity to infinity. Plus minus, why is that the case? Uh, if k is positive, wait, what? Huh. Oh, so it depends on the sign of k. Okay, okay, okay. Understandable. So if k is positive, nothing bad happens. It's still going from negative infinity to infinity. If it's negative, though, you have to put like negative integration from negative infinity to infinity. Okay. Starting the proper order causes a minus sign. Thus, you have this. And this integration that's equal to, okay. I think I'm understanding what they are saying. Fine. But how is this going to prove that del of kx is equal to 1 upon mod of k del of x? I don't know. So this thing is just 1 upon mod of k f of 0. Okay. What about it do? The lower sign apply. So, okay, the lower sign apply when k is negative, and we account for this neatly by putting the absolute value bars around the final k as ingredient. Okay, got it. Under the integral sign, then del kx serves the same purpose as 1 upon mod of k del of x. Just because they serve the same purpose does not mean that these are the same. How can you say that these are the same? Like this would happen for linear functions, sure, but we're not talking about a linear function now, are we? No, we are not. No, we are definitely not. Now, I guess I could create a function such that this would not happen for every x in your interval, right? Yeah. And then I would be able to say that, okay, these are going to different infinities as x goes to 0. And then this would make no sense. Huh. No, you can't just say this serves the same purpose and thus it's the same. That's just wrong. That's just wrong. But I guess it's physics, so it's fine. We can let it slide. But no, like the size of infinity will be different, right? What if it's like a quadratic or something? So then, oh god, this is not going good. Like if it's a function like this, you have a parabola over here, like y equal to k minus x square or something like that. Yeah. So you have a parabola like this thing, or like mod of something like negative x. Nah, something else. Um, yeah, it's supposed to go up. What do you think? Exactly. Whatever. You have a function like this, and right, the way it works is that this. It's kind of hard to give a counter example without going into a lot of details. What function would work perfectly for this thing though? I don't know. Need to think about it. What kind of function would work perfectly for this thing? This should go to infinity. Yeah, I mean we can't be talking about asymptotic functions now, can we? I guess we can actually. It's not that hard to talk about asymptotic functions because like they are going to infinity. The area under them might be finite. So sure, why not? Right? Oh, but that's not the way it should be. No. It's wrong. What about a function like this? You have this two lines and it forms this triangle, right? And then this range is supposed to get to 0, and that as that happens, like this height increases, of course, right? Then yeah, this thing is h. This thing is oh, and then what would be like f of kx in that case? So as you move x over here, you get this thing. Then what about kx? Right. Okay, it's getting complicated really. But I think it's unreasonable to say that del of kx is equal to 1 upon mod of k del x. Yeah, doesn't make sense. Just because they are behaving the same way doesn't mean that this is actually the same thing as that, right? Fine, just move on. Let's try to not use this, thing whenever they show this in action. I'll just go by usual substitution like they did over here to show that this behaves the same as this thing, right? That the del of kx thing behaves the same as 1 upon mod of k del x, right? I'm just going to use the substitution thing that they showed. Okay, evaluate the following integrals. So at 3, of course, is 3 contained in there? Yes, it is. At 3, what's the value of this function? It's just 3 times of 3 times of 3. Okay, just 27 minus what, 6 minus 1. So 26 minus 7, just 20. So that's 20 over there. What about this one? At pi, cosine of pi is negative 1. So negative 1 is the answer. Yes. Then you got at negative 1, well, it's not contained there, so just 0. What about this one? Del of x plus 2, so negative 2 is contained. I think it's just natural log of 1. Yeah, so 0, that makes sense. Hey, how is this going from negative infinity to infinity? Natural log of negative numbers doesn't make sense, right? At least put a mod over there. Come on, are you serious? Okay, 1.44. Evaluate the following integrals. Right, so now they're doing this stuff. Fine, once again, we're going to do the same thing that, we'll just substitute 3x for something else. So let's just say 3x is equal to y. So you just get like del of y over there. Your y equal to 3x. So x is equal to y upon 3. So dx would just be dy upon 3. And your 2x plus 3 thing, that would just be 2 times of y upon 3 plus 3, right? So just 2y upon 3 plus 3. And this integration is now going from, so yeah, like y equal to 3 it goes from negative 6 to 6. Sure. So what does this give us? It just gives us 1 upon 9, 2y plus 9 del y dy. Okay, integration of this thing from negative 6 to 6. So 0, right? F of 0, of course. This thing at y equal to 0 is just 1. So yeah, that's the value. This thing will just be 1. I guess you could just do it the same way like they did. So, the integral would be the same thing as like 1 upon k del of x, right? So, where did that go, by the way? Yeah, this problem. So, just like 1 upon 3 del of x, replace it by that, and the integral would be the same thing. So, that would be going to, yeah, okay. So, just x equal to 0, that's what we want. So, like f of, oh, yeah, sure. Oh, it's still 1, right? So 2x plus 3, that's 0. Sorry, that's 3 at x equal to 0, and then you got 1 upon 3 from this thing, right? So 1, right? 1 will be the value even now. So yeah, it works out. The integral stuff, in the integral, you can assume that these two behave the same way. Otherwise, no, they are not the same functions. Definitely not. Okay, that's awesome. Next, this thing 0 to 2 x cubed plus 3x squared plus 2 del of 1 minus x. So it's negative of that, huh? Interesting. Hey, 1 minus x, huh? I mean, we could do the same thing. We just say like 1 minus x is equal to u and do substitution. I guess that could work. Uh, yeah. Or you could just do the way they are doing, like call it del of negative x minus 1, and then write it like 1 upon mod of negative just 1, by the way. Del of x minus 1, right? Yeah. So just x equal to 1. What's the value at that? It's just 1 plus 3 plus 2. It's 6. So 6 would be this integral, right? Because 1 is definitely contained in this range, 0 to 2. That works out, sure. And what exactly does del of 1 minus x say though? Oh, I think it's just going opposite, right? So you're going from 0 to 1, 0 to 1. So like just say del of x. Del of x has this kind of thing going on. Then del of 1 minus x. That would be just, this thing is x, then this thing would just be 1 minus x, right? So it's like del of this function, right? So as you go over here, that's how del progresses. So it's just this, right? I mean the mirror image of this thing, but at 1. Does that make sense? Whatever, just move on. Yeah, I mean it's symmetric about this 1 upon 2 value, right? It's just put a mirror over here and then reflect this function like this. So for example, if you had some random function f of x, like this thing, and then you said f of 1 minus x, that would be the same as doing this. Oh, I'm bad at drawing this now. Yeah, something like that. So this thing is f of x, and this thing would be f of 1 minus x. Right? Nothing bad, of course. Next. And this was still doable. Okay. What about this one? 3x plus 1. Okay. This is getting bad. Yeah. So x equal to negative 1 upon 3. That's where you have to put that by just 9 times of negative 1 upon 3 squared. Is that contained in the range though? Yes, it is. So just 1 upon 9 over there. And you got 1 upon 3. It's like mod of 3 precisely. Yeah, that should actually work out. You just got like 3 times of x plus 1 upon 3. So yes, it does work out. So 1 upon 3 is this integral. This one. Okay. So at x equal to b. Fine. Oh, so it depends on what a is. Okay. So this will be 1 if b is less than a, and it will be 0 if b is bigger than a. Easy as that. Next question. Show that x 3 upon dx of del of x. Are you serious? A derivative of a function that is defined to be infinite at 0. What? How does this even make sense? Okay, at points where the function is just 0, right? So where x is not in the range where you are actually having the del going to, be non-zero, right? So this is where del goes crazy, and otherwise it's just zero. So in this, like at any point in this interval, of course this derivative is just zero. So like, yeah, it behaves pretty much the same thing as this function. But what about this? Like, what about in this range? I don't know. I don't know what you would say for that. There's no way to think of this because this function is going to like infinity and whatnot. How am I supposed to take a derivative of this thing? A function that is defined by a limit itself that we know nothing of. How am I supposed to take a derivative? I mean, nothing of except the fact that its area is 1. Really? How do you expect me to take a derivative of such a function? Use integration divides, like, that's going to do anything. Look, if I even show that these two are the same under an integral, that does not mean they are the same functions. Why doesn't this book understand this? Whatever, just move on. If they want me to show that the integral is the same, I would gladly do that. I would gladly do that, but that's not what they want me to show. They actually want me to show that the derivative is. And moreover, what does it even mean to take a derivative of like this function? Because the interval is just zero. So when we say like f of x plus dx, what is dx? This is not going good. This is definitely not going good. Like one moment the derivative is like really, really positive and then suddenly it's just very negative. At this point, it's somehow zero. It doesn't make sense. How is this happening? Like the derivative would be if it was this function, that's how del was. Although it's supposed to be a limit, but still, if this was the function, the derivative would be like this thing. It's zero. It drops to zero at this point. It's like it's very positive at this point or something. And then over here, I don't know, is this supposed to be differentiable? Is it even continuous in the first place? I mean, it is continuous, sorry. Is it supposed to be differentiable in the first place? I don't think so. The way it's defined, it may even not be differentiable. So there's no point in taking a derivative. What are these people trying to tell us? No, it does not make sense to take the derivative over here. Wow. Not going good, huh? At one point, it's just very positive, then it suddenly drops to like very negative. It just okay. You might say that's not a bad thing. You have this function defined in this range, but then look at this point. It's zero at this point, and then there's some weird stuff happening. Yeah, this is not looking like a del operator, like the del function at all. Okay, well, this times of x, maybe that would do something nice. Uh, oh god. Oh, it won't. All it's going to do is just flip this upside down. So now instead of having this, you have this thing. How is that the same as negative del? Just move on. Just move on. Okay. Let theta of x be a step function. Show that d theta upon dx is equal to del of x. Okay. So it's 1 if x is bigger than 0 and it's 0 if... okay, I think I'm getting where they want us to go. So usually, like, we won't be able to use the fundamental theorem of calculus if your function is not differentiable. In this case, it's not even continuous, but whatever. If your function was not differentiable, you cannot use, you know, uh, the fundamental theorem of calculus. You cannot use that because the derivative is not defined. But what if we define it to be a del function such that you can use that theorem, although not the way it's supposed to be used, because now you define a completely new function, you just disregard this completely. But fine, I guess you could do so. So think about its derivative, theta dash of x. This thing is 0 if x is bigger than 0. This thing is 0 if x is less than 0. What about exactly at 0? Exactly at 0, it's going from, oh yeah, it's like it's becoming infinity or something. So we kind of don't know what's going on over there. So we'll just say it's like del. So it's del of x at x equal to 0. And this is actually the same thing as saying that theta dash of x is equal to del of x. Now all we have to see is that the integral of this thing, right, from negative infinity to infinity that is actually just 1. We should not even say negative infinity, just some range that, some interval that contains x equal to 0, right? So, the integration from negative 1 to 1 of theta dash of x dx, right? By fundamental theorem of calculus, it would be the same thing as theta of 1 minus theta dash, minus theta of negative 1. But theta of 1 is 1, this thing is 0, so it is just 1. And there you go. Now you can say that, fine, just define. I'm once again saying define, not that it is. I'm going to define this theta function to be del, right? Because it behaves like that. Sorry, not theta function, the theta dash function. I will just define it to be that because it behaves a lot like this. But yeah, just move on. This does not make sense in the first place because it's discontinuous. And I mean, I guess you could do that to make it have nice properties, but honestly, it does not make sense. It's, yeah. Even when we think of it as a limit, what exactly is our sequence? You could have different kind of tells, different kinds of tell function, right? So, for example, if you want to go from this point to that point, right? You could just jump directly upwards. That would be one way to think about it. Right? Your theta function like that could be like this thing. So you have the del being very big at this point, and then it's 0, it's increasing, and then it's decreasing, something like that, right? You could have that. You could have all kinds of crazy stuff going on over here. Things that would seem like just a line to the eye, right? It's like they would feel as if it's just jumped up, but then in reality you could just have like a very smooth curve, sorry, a very steep curve joining these 2 points, right? And there is a bit of like difference in your x coordinates between these, right? Just move on. I don't know. Like both of these have different derivatives, of course, right? One has, okay, actually the first one doesn't actually have a derivative, it's only the second that has a derivative. But then again, you could change the radius of curvature at this point, and then everything will change automatically. Just move on. Just move on. Three-dimensional delta functions. It is easy matter to generalize the delta function to 3 dimensions. Okay, so del q of r is equal to del of x, del of y, del of z. Like, okay, for a cubic volume, then the integral will just be 1. Makes sense, sure. Right, so the notation in all space of del cube of x, okay, that's just this thing. It should not even be all space, it's just some space that contains the origin. Yeah. Generalizing equation 1.92. Once again, del is defined by its integral. So any function that behaves like this is a Dirac delta function. This is just so stupid. Generalizing equation 1.92, where integration over all space f of r del q of r minus a dt. Yeah, okay, got it. As in the one-dimensional case, the relation with del picks out the value of the function f at the location of this point. We are now in the position to resolve the paradox originally. Okay, relation set section 1.51. Wait, what? 1.5.1, whatever. As you will recall, we thought depth of this thing is 0 everywhere except at the origin, and yet its integral over any volume containing origin is constant with, sorry, what? 2 with 4 pi. Okay, these are precisely the defining conditions for the Dirac delta function. Evidently, the gradient of this thing is equal to 4 pi del cube of r. Fine. I mean, I expect it to be some kind of Dirac delta function anyway, right? So let's see what's going on. The volume integral of this thing over any surface that contains the origin, right? Sorry, any volume that contains the origin, that would just be like, okay, for every space that is not the origin, it's just 0 over there, and that's what this del will be. And at the origin, it is going to infinity. It just picks out the value at our origin. So that's just going to be like 4 pi because that's what this f thing is. Over here, f of r, that's actually 4 pi over here, right? And a is 0. Yeah, that makes sense. So I think, yeah, you could say that the divergence is just this thing, 4 pi del cube r, right? Instead of writing del cube, I would still like to write it as just 4 pi del of r, because now we know what we're talking about, right? It's just the 3D data delta function, not the one dimensional. So we don't need this 3D superscript over here. Okay, yeah, whatever, we know that. Okay, evaluate this integral. So it's the volume integral of r squared plus 2 and the divergence of this function, okay, dt, d tau, sorry. So the volume element, okay. Where this is a sphere of radius r centered at the origin. Once again, something that contains the origin. It just picks out the value of this function at the origin, right? Exactly. So that's just 2. Easy as that. It's just, no, it's not just 2, it's still 2 times of 4 pi, because this thing is 4 pi times del of r vector, right? Yeah. So this will just be 2 times of 4 pi, which is like 8 pi. So that's what this integral is. Awesome. Oh, so this was an example, not a problem. Fine. Uh, some other solution. Classical derivative from this thing. Whatever. Just move on. Write an expression for the electric charge density of a point charge q at r dash. Make sure that the volume integral of P equals Q. Electric charge density of a point charge Q at R. Oh, okay. I think I understand that. Should have the volume integral of okay of P equals Q. Got it. Uh, wait, sorry. Volume integral of rho equals Q. Got it. Think about it. Everyone else is just gonna be like that, and then oh, we could just say this thing, right? Our rho of r, that's just equal to q times the delta function at, so it's the 3 delta function, of course. I'm going to write like del sub 3. Instead of using this the superscript, I'm going to use the subscript. It makes more sense. Just del sub 3 of r vector, right? Okay. So then, when you integrate this over this surface, over this volume containing the origin, then yeah, everywhere other than origin this function is just 0, so like that doesn't matter. And then at the origin just picks out this value, so it will just be q itself, of course. Makes sense, sure. Yeah, once again it's kind of weird because we don't know what shape does this function actually have, but yeah, some function of this form that could serve as a point charge. Okay, what is the charge density of an electric dipole? Okay, consisting of a point charge negative q at the origin and a point charge plus q at A. A point charge plus q at A. Huh. Okay, think about it. Oh, we got it like this thing: negative q del sub 3 of r vector, and then just have plus q del sub 3 of r vector minus a vector. Yeah. So at any point other than 0 and so other than origin and a vector, this would be 0, of course. At origin, the integration would just be okay. That's just the negative q. We don't actually know what's the charge density at the origin actually. Whatever. Yeah, that looks cool. Okay. What is the charge density of a uniform infinitesimally thin spherical shell of radius r and total charge capital Q centered at the origin? Beware, the integral over all space must equal Q. Spherical shell of radius capital R. Oh, so like this. So it's actually a finite radius, right? Okay. Huh. This is weird. This is definitely very weird actually. Integral over all space must equal Q. Right. So it's a uniform, right? Okay, the shell is uniformly charged. Fine. This is quite unexpected. Charge density at the the volumetric charge density would not make sense, of course, because yeah, it just won't. Come on, think about it. Because over all space must equal q. Yes, I get that, but now what do I do? What do I do now? Uh, Come on, think about it. Okay, the charge density. We don't actually have a volumetric charge density first place. How do you even measure the volumetric charge density, right? Yeah, that's just stupid, of course. Then how do we do this? Uh, what's the surface charge density? It would just be q upon 4 pi r squared, right? Yes. Let's try to think of this thing. Q upon 4 pi r squared. It's like, this is, yeah, charge upon area. Then, wait. No, it's not making sense. I think this, I mean, this is just a guess, but let's try it out. So del sub 1 of x, and you integrate this. God, this is going to be very, very bad for us. Uh, right. Okay, so this is what our function will be. So this will be, of course, del sub 1 of x. Instead of x, we'll just say r, right? Think of it like this thing. You have got the origin over here. As you move out, your surface charge density here is 0, 0, 0, 0. At this point, it approaches infinity. So that's why I'm thinking it's just del sub 1 of r. That goes like that. Okay, cool. Okay. So then the volume integral, what would that be? Okay, what we could do is just do this times, and of course it should be actually this. Right, that makes more sense. For q upon 4 pi capital R square, because that's actually a fixed quantity. Cool. So this times of our dv element, which I'll just say like 4 pi small r square dr, right? So you know how it's going to be. This is our radius r for our dv element. This thing is, the area is just 4 pi r squared, and then you got dr thickness. So this is our dv element, and when you integrate this thing from r is equal to 0 to infinity, basically that's our integral over the full space, right? Yeah. So that just turns out to be q upon r squared, I think. Yeah, r squared, integration, of course, 0 to infinity, and then del 1 r dr. Okay, awesome. Oh shit, it should be del 1 r minus capital R. Sorry for that. Because at capital R is supposed to be infinite or some stuff like that. Okay, cool. So of course this thing, I mean, okay, it's now like this integral is in one dimension only. So, and this is like a one dimensional derived data function. So like this will just pick out the value of this function at small r equal to capital R. And that just happens to be capital R squared. Yeah, so just get like q upon r squared times r squared. Q. Awesome. That's what we expected. So yeah, this function works. It's just q upon 4 pi r squared, capital R squared. Okay, not small r squared, of course, that would be stupid. And then you got del 1 of r minus capital R. Wow, sometimes you just have to take random guesses and this works out. Honestly, I didn't think this would actually work out because it was completely random. I just thought that okay, something like one dimensional would work because you already got area in the denominators, like that's two dimensions done, and then you just want one more or something like that. But somehow it worked out, although there was no real reasoning behind it. Fine. Okay, well, let the following integrals. Okay, integration over all space of this thing r squared plus r vector dot a vector plus a squared, and then you got this del cube r minus a whatever. Just picks out the value at a vector, put in a vector for this function. What do you just like a squared plus a squared plus a squared is 3a squared, of course. Okay, Then the integration over volume, well, okay, this is a cube of side 2 centered at the origin, and p vector is this thing 4 comma 3. Also, this vector is actually not in our cube at all. Huh? Yeah, it's not in the cube. 4. Wait, okay, it's like 4y hat plus 3 z hat. Got it. This cube is given by this region. So any point that follows these three inequalities, x less than or equal to 2 bigger than or equal to 0, y less than or equal to 2 bigger than or equal to 0, z less than or equal to 2 bigger than or equal to 0, that falls in or on our cube, right? And this does not follow this inequality, which means it is not in our cube, it's outside of the cube. Okay. Uh, okay, cool. So we'll never have that thing actually. Hey, what do you have over here? Oh, I thought this would be inside the delta function. It's not. It's not actually. Huh. It's got this thing. Okay, you got 5r vector, del cube of that, and then you got d tau and all that stuff. Okay. What do we do now? 5r vector. It's not like just one-dimensional integration where you can just say, yeah, that probably won't work. So now what do we do? Still try to think of it. What you could say is like 5x is equal to u, 5y equal to v, and 5z equal to w, and let's see what happens. So this will be like, okay, and I'll just say like capital R vector that's equal to u comma v comma w, right? Then this integration, this is the integration of r vector minus b squared. It's like okay, what's r small r vector? So a small r vector, of course, is just r vector upon 5. So it's like that's the thing. R vector minus 5. Oh, upon 5. Sorry, upon 5 minus b, this vector, and then that thing squared. Okay. Yeah. Then you got del cube of 5 r vector. It's like what? Del sub 3. I think I should say that. Okay, and it's just del sub 3 of capital R vector, and our d tau is like dx dy dz. Now it's like 125 du dv dw, right? Oh wait, no. U is 5x. Yeah, okay. Wait a second. Sure. I think I get what's going on. Yeah, okay, U is in fact this 5x. So fine. Our dx dy dw would just be like du dv dw upon 125. Cool. So that's our d tau now. Du dv dw upon 125, and this is like the volume element in our new system, right? So then mathematically this thing is the same as a volume integral, although like uvw are not really what our coordinates should be, but whatever, this is still the same thing mathematically. So then yeah, awesome. Hey, first of all, actually simplify this thing. What do you get? You get like the integral over some volume. This gamma volume is different from this gamma volume. So this is gamma is a cube of side 2 centered at the origin. Now our gamma is like what? So our inequalities were like x less than or equal to what was the thing? Yeah, x less than or equal to 2 with 2 0 somewhere. So since x is u upon 5, right? It's got u less than or equal to 10, greater than or equal to 0. Right, so now this thing is actually a cube of side 10, right? Of course. So actually this integral, you can replace it by this triple integral from u is equal to 0 to 10. This is v is equal to 0 to 10, w equal to 0 to 10. And then you got this stuff. Oh, and now actually del cube would make sense, right? Because you'll just get this thing. It's like what? First of all, simplify this thing. It's just r vector minus 5p vector squared. You got 1.5 squared as 5 cubed, just 1.5 power 5. And you got du d okay, d tau basically. I'm gonna write d capital D because you already used tau for that. Okay, and this del sub 3 function. You can actually split this as one-dimensional direct delta functions. So it's like del 1 of u, del 1 of v, del 1 of w, like that. So that's our new integral. Okay, awesome. Ah, just put that over there. I mean, you get it, right? Just gonna put that over there. Whatever, you get the thing. I just don't have space to write that. So what will you get? I mean, these functions are going to spike when you have, yeah, when you're at the origin, right? So at 0, 0, 0, like u equal to 0, v equal to 0, w equal to 0, that's the value that you want, of course. Yeah, that makes perfect sense, of course. Although it's kind of weird that we have just a cube of side. Wait a second. Oh shit. So if I think about a direct delta function like this is, yeah, okay. So we know that the integral over an interval that contains this range, that will give us 1 for a delta function. But what about an interval like this? So it's going from 0 all the way to some things like some a. Is this like half or 1? Which of these? Because if this is like actually symmetric in this range, then you would say it's just half. If it's not, then wait, isn't it supposed to be symmetric though? See, that's the problem. You don't actually have a nice definition for this function. That's why we have all these problems going on. This made perfect sense to think about the integral of this function when our interval was not having 0 as its lower boundary or upper boundary. But now it's complicated. I mean, what if your function is more inclined to the right side, and what if it's more inclined to the left side? How would you know which of these regions gets the bigger part? There's no way to know. It depends on how you define this function, right? So just talking about this thing without context, no way, I can't solve this. I cannot solve this basically. Oh, okay, I think, got it. It said centered at origin, not that its vertex is at the origin. Oh, of course, that makes perfect sense. So then when it said side 2 and centered at origin, it's like x is less than or equal to 1 and bigger than or equal to negative. But hey, that's a good thing because now we know what its shortcomings are. But whatever. So like that's the same thing as saying u is less than or equal to 5 and negative 5. Whatever. This changes. This changes to this thing. Negative 5 to 5, negative 5 to 5, negative 5 to 5. Awesome. And yeah, now we can definitely say that this, just pick out the value at 0, 0, 0, and that's it. So at 0, 0, 0, just get like this thing is just 0 minus 5 b vector squared. So 5 squared upon 5 power 5, and then you got b squared. Yeah. So that's 1.5 cubed b squared. What's b squared? What's the value of b? So b squared is 25. Cool. So it's just 1.5. Yeah, 1.5 is the answer to this. Okay, cool. Next. Okay. So this is the speed of radius 6 about the origin. C is this vector, whatever. C is the magnitude. C vector. What's the magnitude of C, by the way? I mean, what is this small c? It's just like square root of 25 plus 9 plus 4. Seriously. It's like 13 is per square root of 48. So, sorry, 38. What am I doing? 38. Not a good thing. Definitely not a good thing. Okay, and what's our sphere radius? 6. Okay, it's like sort of 36. It's more than that. Oh, so it's lying outside our sphere, and this whole, oh, that was easy actually. This complete integral is, huh, yeah, very easy. This point c vector. This actually lies outside our sphere, so we never reach that. This thing is going to be 0. I get that. Next. Sphere of radius 1.5 centimeter 222. So it's about the origin. This thing is different now. It's at 222. And then you have del cube of E minus R. Okay. So E is what? 3 to 1. What's our D thing though? I don't know what that is. Whatever. So E is equal to this guy. Okay. Is this inside our sphere? So from 2 to 2, what is the vector? Is just 1 0 1. So it's 1 0 negative 1. So square root of 2 is the length. And yeah, that's less than 1.5. So it's inside our sphere. Okay. Then at R equal to E, we'll just get this thing. Got it. Got it. Of course, it's just going opposite. You get the thing, right? We have done that before. So, this picks out the value at R equal to E. So our value would of course be just E vector dotted with E vector minus, sorry, D vector minus E vector, which is E dot D is like 3 plus 4 plus 3, and then minus E squared, which is just 9 minus 4 plus 1. Oh, it's minus 1. It's negative 4. That's our answer, huh? Yeah. Of course. D vector minus E vector over there. It's negative 2 comma 0 comma 2, right? Whatever. Still just checking it once again. Yes, it is negative 4. Okay, move on. Evaluate this integral. Which is a sphere of radius capital R centered at the origin by two different methods as in exercise 1.16. Fine. So it's a volume integral. Okay, this is a sphere of radius R centered at the origin. Okay. I think I get it. It's just going radially outward, right? I mean, yeah, sure. So what do you think? What if like I could write this as a divergence of some other stuff? That would make much more sense, of course. Um, but what? Divergence of that. Come on. It's like two different methods that could be a problematic thing. Sure. We just have to do it using the direct delta function. There's no other way. So what you get is get like 4 pi e power negative r, and then you got del sub 3 of r vector, I should say, or whatever. Or theta of dv, I like to call it. This volume integral, right? Yeah. So at 0, just plus out the value at 0, of course, which is 4 pi e power negative 0, just 4 pi. So 4 pi is the thing. Cool. And you also want some other way of doing it. Okay. So what is exercise 1.16 telling us? Where is that? Of course, using the direct delta function, and solution 2, we transfer the derivative from r, okay, to r squared plus 2. So the problem was this thing, of course, and then you changed this, okay. Oh, it's like, okay, integration by parts, it seems. Fine. Fine, fine, fine. That's integration by parts, of course. Okay. Yes, I could use that. But what about this one, though? Like this gradient. Uh, okay, let's do our r hat. Still, what about it? Oh, that is good. Okay, 2 upon r d tau. So then you can convert this to a given spherical coordinates for it. Still very weird though. Drawing of the formula of the office P where R is equal to capital R, D A is equal to R squared sin theta d theta d phi R vector. So the surface integral becomes this thing. Putting it all together, then 4. I get that. Uh, yeah. So the area element you actually told us, you also have the volume element over there actually. 4 pi R squared. Fine. We just want the volume integral, sure. So why are we talking about the surface? Oh, for the second part. For the second part, okay. So this is like divergence of something, it seems. Yeah, okay, the divergence of complete. Got it, got it, got it. Yes, you can use the similar thing over here as well, I guess. Sure. So this is why you have this circle over here. It's a, yeah, it's an integral over the surface. Cool. Okay, let's try it out. Let's see if we can do that. So we want to evaluate this integral through the same method. Let's see. So the divergence of what was the thing once again? Divergence of f times g. So f and g are vector functions. I should just say a vector. Wait, no, these are not vector functions actually. Wait a second. Oh, it's like this thing. Divergence of a scalar function times another vector function. Right, that was the thing, of course. Yes, yes, I think that was the case. That can be written as what? Um, just dot it with this guy. Yeah, just like f us. Okay, it's the partial of that guy, which is just right, right, right. You can write like this thing. Write it as the gradient of f that dotted with u vector plus the yeah plus wait, was that a thing? Yes, plus f times the divergence of our u vector itself. Right, that's what you can do. So over here the thing we're getting is like this term. Okay, so we can write it, we can rearrange this equation. F divergence of u, that is just equal to the divergence of f times u minus divergence or minus the gradient of f with u vector, and then we just integrate this thing. Let's put theta over there, whatever. So equal to this guy's integral theta as well. So what do you get? Well, this first part is just now like using Green's theorem or whatever it's called, that the divergence theorem, of course. This is just the surface integral of the boundary. Yeah, okay, whatever. So this is just equal to the surface integral. This is the volume integral, of course. Surface integral over the boundary. So you got the a vector, whatever. Then what you got? You just got f times u vector. Yeah, yeah, that makes sense. Sure. The flux, and then minus this integral. And it's still in the volume. Okay, let's try it out for this thing. In this case, our f thing is just e power negative r, and our u vector is r hat upon r squared. So the thing we're looking for is this: the surface integral over the boundary of this surface, of course, which is the yeah the hollow sphere. Fine. Of f u vector is just e power negative r, and then you got r hat upon r squared. And then you got dr vector. Wait, no, okay, sorry, the dA vector. Fine. Oh, it's supposed to be dot product, right? Yeah. The flux, right? Hey, we are in luck today because A vector is actually dA vector is pointing along our r hat. So like this thing is just the same thing as dA times that. Cool. Guess what? Throughout the area, yeah, throughout the integral, this like these values just stay the constant because it's a constant radius thing, right? Awesome. So first part is just e power negative capital R upon r squared, and then well dA is like 4 pi r squared. Okay, got it. It's 4 pi over it. Right. Hey, we did this before as well, right? What was the answer that we got? I don't remember it though. 4 pi e power negative. Yeah, right. Just 4 pi. Just 4 pi, right? Exactly. Yeah. I think that was a thing. Just 4 pi. And this is we are getting like 4 pi e power negative r or something though. That's weird. The volume integral should be equal to the flux. Yes, yes, that makes sense, but this is not going the way I thought it would. Is this really correct? It has to be, right? Add r equal to 0 is like 4 pi and then 1. Yes. Just complete it and we'll see what is the thing. So you got 4 pi e power negative r over here. What about this one? So minus e vector, the gradient of this guy. What's the gradient of e power negative r though? Um, yes, like just e power negative r negative of this guy, then dr upon dx. That turns out to be just x upon r all the time. So negative e power negative r upon r and then just x y z like that, just r vector. So all you get is like r hat. Awesome. So that's the gradient, and if we don't want to take a dot product with our u vector thing, which is just this guy. So this dotted with r hat upon r squared. Oh, this is nice. So all you get is like e power negative e power negative. I think it's positive only. Negative e power, sorry, e power negative r upon r squared. Then you got d tau. Yeah, awesome. And of course, this is over the whole sphere. Now d tau, I would like to change that so we can write it like this thing: 4 pi r squared dr. This cancels. Just get like 4 pi division of e power negative r dr or whatever, and it's going from r equal to 0 to capital. Oh, I think I get where it's going to cancel out. Fine. This integral is just like 4 pi, like negative e power negative r going from 0 to r. That's the same thing as e power negative r going from r to 0. So add 0 is just 4 pi, and then it's like negative 4 pi e power negative r. Yeah, that cancels with this guy. It is 4 pi in the end. Awesome. So there we go. In both ways, it's 4 pi. Still weird though. So all of this actually relies on the fact that this guy's divergence is, yeah, okay, on the divergence theorem, of course. I think under a limit, this equation would make sense, but when we think about it as like finite values, this does not make sense immediately. Fine, I'll let it slide as long as it's giving us the correct result every single time. I think it's good to say this equation is true, right? All the time. I think so. Anyway, let's move on. So 1.6, the theory of vector fields. The Helmholtz theorem. Ever since Faraday, the laws of electricity and magnetism have been expressed in terms of electric and magnetic fields, E and B. Like many physical laws, these are most commonly expressed as differential. Oh, fine. We're getting to the real thing, right? The Maxwell's equations. Okay, since E and B are vectors, the differential equations naturally involve vector derivatives, divergence, and curl. Okay, indeed, Maxwell reduced the entire theory to 4 equations, specifying respect to the divergence and curl of E and B. Okay. Maxwell's formulation raises an important mathematical question: to what extent is a vector function determined by its divergence and curl? In other words, if I tell you that the divergence of f, which stands for E and B, as the case may be, is specified scalar. Okay. So this is happening. The divergence of this vector field is given, and the curl is also given, right? For consistency, C must be divergence. I mean, that makes sense, sure. Can you determine the function f? Not quite. Okay. Why so? For example, as you may have discussed problem 1.19, there are many functions whose divergence and curl are both 0 everywhere. Okay. Trivial case f equal to 0. Then there's of course our r hat upon r squared. Yeah, that case. And they also are giving us some other cases. So you got f is equal to yz x hat plus zx y hat plus xyz hat. Okay, fine. Yeah, its divergence is 0. What about the curl thing? I guess that will be 0 as well. Yeah, and you got all of this stuff. To solve a differential equation, you must also supply it with appropriate boundary conditions. Okay, in electrodynamics, we typically require the fields go to 0 at infinity, far away from all charges. With this extra information, and the Hamilton's theorem guarantees that the field is uniquely determined by the Lavoisian curve. Proof of the Hamilton's theorem is given in Appendix B. Okay, so if the field is going to 0 at r equal to infinity, then your divergence and curl, well, they determine the function itself. Interesting. Yeah. Can I prove this right now? I don't know. Um, I don't think so. I'll have to spend a lot of time thinking about it if I want to prove this. Because if it's named after somebody, that means he must have like spent hours and hours trying to figure it out, right? That's why like this got popular. Anyway, so I'll see you guys next video. I'll try to read this and then explain it if I can. Goodbye.